So what we want to do today is press on with time domain system analysis. So what we're doing, context here, time domain system analysis. We're going to be spending a lot of the quarter doing system analysis, where again, system analysis is you give me some system, some description of it, and an input, and maybe some initial conditions, and I have to tell you what comes out. And so far, and we can do that both in the time domain and in the transform domain. We're starting out in the time domain. We already have one technique for doing that you've been practicing, which is recursion, a table method. That gives us sample values of the output, and it mimics what the actual processing that would be going on in that digital signal processing kind of system. You take in some new information, you process it, spit out a new output, go get the next one, and on and on and on. So that's perfectly valid for finding actual sample values. What we're going to work on today, though, is coming up with an analytical solution. Meaning we're going to describe inputs and outputs in terms of functions of n. And for that, our first technique, mimicking how we did this with continuous time systems, is we're going to have to solve some equations. In this case, not differential equations, but difference equations for a particular input and a particular set of initial conditions. And that will give us not just sample values, but an expression for y of n that we can plug in n values and get those sample values out of. And then we'll move from that eventually to convolution using this unit sample response. And then we'll move on to the transform domain. And so where we're at today is right here. Method number 2. It's going to take us all of today and a little bit of Monday to thoroughly go through that. And depending on who you had for 228, the description that I go through today of how we're going to solve those difference equations may sound really familiar. In fact, it's like exactly the same way that we solved differential equations in our system context, except now we're going to use these same methods for solving our difference equations. But the terminology is the same, the lingo is the same, the way we attack the problem is all the same. And again, the long game is, it's going to be a struggle. Get ready. It's going to take a lot of paper to do these solutions, and then it's still going to take a lot of paper, and then we're going to move to the transform domain, and it all gets much easier. But we got to slog our way through the time domain first. So that's what we're going to be up to today. All right. So how does this work? Well, first of all, before we do anything, we've got to walk up to our system, look at its difference equation, and say, is it linear or is it time invariant? Or shift invariant in this case. Because if it's not, the method don't work. The method assumes linearity and assumes shift invariance. If I have a linear LTI system, linear shift invariant system, then we know the difference equation has a very particular form. It's like this in general form, where all the coefficients of the x's and y's are just numeric constants. And that kind of linear time-invariant difference equation I can solve using the method of undetermined coefficients that we're going to go through today. So first, got to check the equation, make sure we're got the right kind. And if we do, all right, we can proceed. Now, this difference equation is a system description. It contains all the information there is to know about the system and its dynamic behavior. It completely describes the system. It tells us the shape of the natural response. It tells us everything about how it's going to respond. Is it underdamped, overdamped? Is it first order, second order, third order? all that's in there. Where is it? Where do I find the key to unlock that system in there? What part of that difference equation's got the thing that makes one system act one way and another system act another way? Where does that live? No, you're just afraid to say it. What would be different from one system difference equation to another? It's Friday, it's 4 o'clock, don't make me think. It's in the coefficients. It's in the numbers. The only thing that changes from one difference equation to another is what A values do I have, what B values do I have, and how many of them each do I have. That's it. That makes the system, whatever order it is, determines the shape of the natural response. It's all in the coefficients. So it differentiates one system from another. And so using those coefficients, we're going to need those to do this solution of our difference equation. Find the response. It's going to rely on those coefficients somehow. And so what we're looking for is, what is the output for a given input? Well, this is a description of the output in terms of the input, and maybe delayed inputs, and maybe fed back outputs. But this is an input-output relationship kind of description. And the dynamics of the system are captured in the numeric values that we have in these coefficients. Right. So if I want to solve that difference equation for the output for n greater than or equal to 0, I should say, we're going to do that for a particular input x of n and any existing initial conditions, which initial conditions in our discrete time system are a little different from the continuous time. In continuous time, I needed to know, like, derivatives. Well, here in difference equations, I need to know previous values. Like, what was the previous value of the output at index n equals minus 1, and index n equals minus 2, and so on. So our initial conditions are simply initial values of the output at previous instances in time, starting at n equals minus 1 and moving back to however many we need. So you give me an equation, you give me enough initial conditions, give me an input, this starts at n equals 0, output should come the output y then in an analytical form. That's what we're trying to achieve today. Okay. Now, what's going on in these initial conditions? What are they all about? Well, it was a little harder maybe to imagine or to visualize before. Let's lose this. And we're going to take a particular example through this process. And so let's do that. Let's just set up a problem here. Y of n equals x of n plus x of n minus 1 minus 1 half y of n minus 1. There's a difference equation. Is that linear? Shift invariant? Causal? Dynamic? Yes. Recursive? Yes. Okay, I can do it. As soon as I said linear and time invariant, I could stop asking questions. As long as it's that, I can go ahead. I was just curious about it. Okay, let's draw a little block diagram. So we have x of n going in, and let's see, we're multiplying that by 1, we're delaying it by 1, and we're multiplying that by 1, and we're adding those back together, and we're creating a y of n, which I know I'm going to need. Well, I'll cheat. Y of n coming out, but I got to delay y of n once, and multiply that by minus 1/2. And I'm going to add that back in there. I'll just make a big summing block there. And I've got my system. And I put in a bunch of x of n's, and out comes a bunch of y of n's. And okay, So, initial conditions, outputs of y before I put in the new input. Yeah?
Do you need the multiplier, or can you?
I could just have a piece of wire because they have to be one. But I'm
Okay.
being general here. Could have been a 2 there. If it was a different difference equation, I would have had a coefficient. So yes, I don't need those. But we'll keep them in the picture. So where do these initial conditions come from? How could this output have some values before n equals 0? Well, there must have been some past inputs. Somebody put something other than 0 into this system before, and the output was finishing its response to that. Now, why is that happening? Well, notice in our system, x of n minus 1, we have a y of n minus 1 term in here, that even if I shut off the input, there's an old value sitting inside here that's still affecting the next output. And the same thing here. Even if I shut this off, there's still an old output that's working its way back in. So unless this system is such that all these delay units have zeros on their output, there's values coming out of this that are caused by stuff that's already in the system. Right? That's what the initial conditions are telling me about. They're telling me there was stuff, somebody put something in before, the numbers are still working their way through all the shift registers, we're not done getting it out of the system, it's still responding to it, in particular about feedback from the output. There could be some long transient responses that go on for a while. And so I need to account for that. I'm going to put in a new input at time n equals 0, but part of the response I get is going to be due to the new input I put, and part of it's going to be because there was some leftover stuff still working its way through the system. So what we're going to do today is parse the output between those two. We're going to separate them out. Now, if I have an n-order difference equation, I need n initial conditions to come up with a complete solution. What order system do I have? I hear 0 order system. Anybody disagree with that? First order system. Find the highest delay on the y side, right? Wherever it shows up. So this is a first order system. So I need one initial condition. And the first initial condition is always y at index n at index minus 1. For our example, we'll use initial condition of the output at n equals minus 1 having a value of 2. And what we're going to want to know is, how does this system respond? What comes out of this system if I already have this initial condition just before I apply a new input, and then I apply a new input, x of n equals 2u of n. Right. So my x of n is a double-sized unit step. So it's 0 for n less than 0. At n equals 0, it jumps up to 2, and then stays there forever. A big step. And I want to know, what's the system going to do coming out? What's the shape of the output going to be? What's the total response going to be? Some of it's going to come from the fact that I hit it with a new input. Some of it's going to come from the fact that there was some leftover stuff inside here. I want to take a guess at what the output's going to look like. Based on your vast systems knowledge. Don't ask those questions on Friday. Just don't do it. Well, okay. Well, we'll talk through it and see if we can't kind of feel what pieces are going to come here. Well, let's see. If I put a step into a system, what kind of response do you get out of a step?
response?
Yeah, yeah. It's kind of steady. Well, it's part of it's transient, part of it's steady state. It shows up in steady state. But what shape would that have? That's one. None of that. What shape would it have? You think? What's a good guess? Okay. I'm guessing I put a step in. I'm gonna get a step out. I'm thinking, especially in a first order system. I'm thinking. But we'll see. Okay. All right. If all my initial conditions are 0, we call that a relaxed system, meaning all of these delay units have zeros on the output. There's nothing adding in here. Only new stuff is going to make this system respond. So if all the initial conditions are 0, we have what we call a relaxed system. All right. Now, we can always break up the total response of a system into 2 components, a forced response and a natural response. Natural response, that's caused by, the shape is caused by the dynamics of the system. Now, back in continuous time, we said, it's like, you know, if you've got a mechanical system, you might have a spring and a damper and mass, and these kind of physical things determine the shape of the natural response. Well, equivalent here, the dynamics of the system are inherent to its design. It's actually embedded in the A coefficients, the ones on the right side of the equation. I guess I don't really have this in the right form to see. Let's rewrite this. Y of n, let's bring that, all the y's to one side, and all the x's to one side. So our equation would be y of n plus 1/2 y of n minus 1 equals x of n plus x of n minus 1. Same difference equation, just rewritten in our standard form. The A coefficients, well, there's A0, here's A1, here's B0, here's B1. Well, these guys are 1. This one happens to be 1/2. But it's these coefficients, this 1 and this 1/2, that are going to determine the natural response of the system, the A side coefficients. And all those natural responses for these linear constant coefficient difference equations, all of the natural response forms are going to be some kind of exponential. Because an exponential is the only function that's a solution of this particular structure of difference equation. Now, that could be an exponential with a real exponent, an imaginary exponent, or a complex exponent. So we can get the same kind of forms we got in continuous time systems. We can get decaying exponentials, we can get oscillations, or we can get oscillations with real exponential decays. And so, yeah, but this is it. This is the whole range of possibilities. Some number to the n, maybe n times some number to the n, or n squared, a cosine or sine with n as our index, or maybe a cosine with an exponential out in front. And those are our only options. Okay? And which of those we get, those exponents, those exponential terms, are determined by the roots of the characteristic equation of the system, of the difference equation. Oh, we had that before too. Huh. And where we get this characteristic equation from is, again, take the left-hand side, and we're going to rewrite it with not a differential operator, but a delay operator. The same one we're using in our picture. Z to the minus k. Z to the minus delay. A z with an exponent that matches up with the delay in the y terms. And we're going to rewrite the right-hand side of the difference equation using that operation. So, for example, a y of n minus 1 becomes a1 z to the minus 1 operating on y of n. And a y of n minus 2 term becomes a z to the minus 2 operating on y of n with this coefficient out front. Then we strip out the y's and leave a polynomial expression in our new operator z, whose coefficients are exactly the same as the coefficients of the difference equation, the right-hand side, these guys. We We find the homogeneous solution by setting that equal to 0, and then maybe multiplying through by powers of z to make it easier. Factor that, and we get the roots of this. This is the characteristic equation of the difference equation. Factor it, those roots are the things that are going to tell us what kind of natural response shape do we have. We'll have some, so it'll tell us what shape we have in the natural response, and then we'll have a bunch of unknown coefficients. Those will solve for the particular input and the particular initial conditions to get those unknown coefficients. Well, we could do that. We're not going to do that, but we could do that. But that's the natural response piece. The other piece, the forced response, is determined by, well, all the forcing functions, all the input signals that we're going to be interested in turn out to be things that are eigensignals for our linear time-invariant system, which is a fancy mathematical word that says the shape I put in is the shape I get out. That's why I could say, hey, you know what? The response to the system to my little step is probably going to include a step, because the forced response to the system will have the same basic functional shape as the input signal for the ones that I'm likely to put in. So we have a table where we look up. If I put in this function shape on the x of n, here's what the forced response looks like. If I put this flavor in, I get this kind of forced response. So we can look it up, what the basic shape is, again with some unknown coefficients. And to find those coefficients, well, that forcing function by itself has to be a solution to the difference equation. And so we'll use that and the actual input to solve for the unknown coefficients. If I add the natural response to the forced response, I get the total response. That's one way to look at it. Yeah. So we add those two pieces, forced response and natural response. Use the initial conditions to find the missing coefficients, and voila, out pops the answer. And that's how your book tells you to do it, at least the first way the book tells you to do it. That's probably how, if you did anything like this back in RLC circuits, well, you didn't do it with difference equations, but you did something parallel to this with differential equations. But that's not what we're going to do. We're going to say, take the same deep tour you probably took in 228 and say, I don't like that way. I can solve a whole lot more problems if I break up the problem differently. Instead of forced response and natural response for my two pieces, I want to break it up into zero state response and zero input response. Okay. Who remembers what those are? Or what the name implies? What's a zero input response? Initial condition? Initial condition is 0. Zero input? That means zero input. Zero input response is response to the system if there was zero input. What a clever name. If there's zero input, what's it responding to? Initial conditions. Yes. The zero input response is all the response that comes from just the initial conditions, as if I never put a new input into it. We isolate that here. The zero state response is the response of the system to just the input, as if there were no initial conditions. So we're going to separate those two pieces. Isolate the part of the response that came from the fact that I hit it with something new. Separate it from the part that some of that response came from, there's leftover junk in here that isn't done yet. And I want to parse, separate those two pieces. Zero state response is response as if the system had a zero state. It was relaxed. It had all zeros inside. Zero input response, as if I shut off the input and whatever's left in here just finishes grinding away. So we're going to separate out that way. Not forced natural, but zero input, zero state response. The zero state response assumes a relaxed system, even if there wasn't. And zero input response assumes there's no input, even if there is. but lets me break up the pieces and separate them in a way that's helpful for solving the problem. Okay. Now, zero state response sounds a little bit like the force response. It's a response to the input. Well, it's not exactly the same thing. It includes the force response, but it also has a piece of the natural response. If I hit a system with a new input, I get a steady state response, I get a forced response, but it's also going to give me a transient, right? That transient response shape is dictated by the natural response of the system. So I'm going to get a piece of the natural response here. The zero input response is pure natural response, but only a part of it. The part that wasn't done, it wasn't finished working itself out from previous inputs. Okay? It means that the zero input response has the same shape, the same functional form as a natural response, but it's probably a different coefficient out in front. The total natural response is going to be broken up in two pieces. Part of it goes with the zero input response, part of it goes with the zero state response. Now, just said like that, it sounds like I'm making things more complicated, but it actually makes the solution easier. If I wanted the total natural response, I'd have to extract the piece that was down here in the zero input response, add it to the piece that was up there in the zero state response. Okay. Still with me? In the zero input response, we solve, again, assuming the system is relaxed, meaning we assume all the initial conditions are zero in the solution. As we're trying to find the unknown coefficients, this will be our assumption. When we find if the system is truly relaxed, there are no initial conditions, and there will be no zero input response. Make sense? No initial conditions, no zero input response. And everything is a zero state response. Whew. A lot of words. How are we doing? Okay. Let's go through introduce the method. What we're going to do is walk the problem through as we describe the method. Nth order linear constant coefficient difference equation, so nth order we get from the right hand side, has a single input case that looks like this, meaning we'll talk about this a little bit more, but we're going to simplify the left hand side a little bit. We're going to go after the characteristic equation. Again, the characteristic equation comes from replace all of our y terms with z operators. For the exponent matches the delay in the y term. We keep the coefficients that are on that side, and then set that polynomial equal to 0 to find the homogeneous solution. Again, the z minus k is the delay, matches the delay of all the y's. We don't like negative exponents, so we'll multiply through by z to the n and get a positive exponent polynomial that we can then set equal to 0 and factor. All right, so let's take our example. We've already set this up, and let's walk it through the problem. First, we're going to find the zero input response, and I'm going to turn the lights up so we can see what's going on the board. And I hope you can still see what's on the screen. I want the zero input response. Zero input response. Response of the system to zero input. Okay. Then I'm going to find the forced response. And then we're going to find the zero state response. Then we're going to generalize the zero state response and add it to the zero input response and find the total response. That's the method. So, zero input response starts with a characteristic equation. So we're going to take our rewritten standard form difference equation, take just the left-hand side and write this with the z operators. So y of n has a coefficient of 1 out in front. That's like a z to the 0. Plus 1/2 z to the minus 1 for the n minus 1 term. And that's it. Set it equal to 0. And I don't like negative exponents, so I'll multiply everything by z, and we have a z plus 1/2 equals 0. So that means z equals minus a half. So we found the characteristic equation. We set it equal to 0. We factor it, and we find the roots of the characteristic equation in order to find the 0 input response. So that's our first step, find the roots of the characteristic equation. And then the form of the natural response, which is also the same form as the 0 input response, is determined by what kind of root we got. See table 1. All right. Here's table 1. I got a what kind of root? This is a negative real root. So I look up real roots, and it says my natural response has this form, some unknown k times the root I got raised to the n power. So the 0 input response, which has a form of the natural response, has a piece, I'll put a 1 there, a piece of the natural response, not the whole thing, has a form k minus 1/2 to the n. If I had gotten a complex conjugate root, I would have pulled out this expression here. If I got repeated roots, I would have gone up here. So we go in this table to see what form we get. And the root itself is part of the solution. Still with me? Okay. Now, I've got an unknown k. I need one way to solve this. I have one unknown. I need one initial condition. Since I'm finding the 0 input response, which is the response to the initial condition, I'm going to use the bona fide, real, honest-to-goodness initial conditions to solve for this unknown coefficient. So what was our initial condition? Y of minus 1 was plus 2. So I plug in n equals minus 1 to here, and equate these guys. Let's see, negative exponents mean I flip things over, so I think this is minus, same as minus 2k. So minus 2k is plus 2, therefore k must be minus 1. And my 0 input response then is a negative 1 times minus 1/2 to the n. That's true for n greater than or equal to 0. So let's put a u of n after that to handle that. And we have our first piece. 0 input response. Okay. So we took the difference equation, we found the characteristic equation from it using the delay operator, substitute for the delayed values of y. We only took the y side. We took that operator characteristic equation, set it equal to 0, found its roots. The roots told us from the table what flavor we had for our natural response or our 0 input response. Had an unknown coefficient, needed an initial condition. For 0 input responses, we use the real initial condition. The real McCoy. Well, we got to be careful. I'm using real in a couple different ways. Actual. Using the from there. Questions? Are okay on that part? 1/3 of the way there. Okay. Now we need to find a 0 state response. That's the response of the system to just the inputs. No initial conditions. Unfortunately, where's my difference? I cannot find easily the 0 state response for this equation. That's a shame. However, I can find the 0 state response for the single input case version of this. single input case, which is a simplified version. The y side stays the same, y of n plus 1/2 y of n minus 1, but all I'm allowed to have on the other side, on the right side, x of n. Literally a single input. This one I can find, the zero state response. So we're going to find the zero state response for the single input case. How do we do that? Okay, follow the cookbook. Find the force response. The form of the force response is determined by the forcing function. All right, let's come over here. Find the force response. I f of n. Where do I get that from? See table 2. There's table 2. It says, if you put in this shape for an input, here's the shape of your force response. If I put in this shape, here's the shape of your force response. We put in, for time, for indexes n greater than 0, we put in a constant. N greater than 0, x of n equals a constant. It's 2, right? So according to my table, force response must be a constant. I don't know what constant, but a constant. Okay. So we just look that up. How do we find that constant? Substitute the force response into the single input case difference equation that includes just x of n on the side, and solve for the unknown coefficients. So that this force response has to be a solution to yf of n plus 1/2 yf of n minus 1 equals x of n. So I took my single input case difference equation, made it the forced response as the output, and I'm going to use the real input. Yf of n is a constant. 1/2 yf of n minus 1, I contend, will also be 1/2 times a constant, equals x of n. Well, for n greater than 0, x of n is always 2. Now, let me help you with this one. If my output out here is 5, and the output is constant, the output at the previous output is also 5. Also. So if I go out far enough, this and this should be, if it's a constant, should be the same. So what do we have? We have 3/2 of C1 is 2. So C1 must be 4/3. So my forced response, let's put it down here, is 4/3. And if you like, that's true for n greater than 0, because I'm putting in a step function that starts at n equals 0. Sorry, trying to make it readable and make it worse. U of n. How's that? Okay. So we found the force response of the single input case, and we're running out of time. How do we do that? How do we do the rest? Find the zero state response. It's the force response plus a natural response. Oh, I already know the shape of the natural response. Let's go over here. I already know the natural response has this shape, right? So let's go over here. We're still finding the zero state response for the single input case. we'll call that YZS1, so I remember it's a zero state response. It's a forced response plus a piece of natural response. Forced response I got, 4/3. Natural response has this shape. Different coefficient, but the same basic functional form. Okay. Solve for the unknown coefficients using the initial conditions that are appropriate for a zero state response, which is all initial conditions have to be zero, because I'm doing a zero state response. So Y zero state response for the single, that's Y, call it YZS1 of -1 has to be 4/3 plus K2 times -1/2 -1. 4/3 minus 2 K2. Let's cut to the chase. K2 then in that case is, that's forced, is 2/3. Plus 2/3 times -1/2. And then here's my zero state response for the single input case. Everybody okay? So we found the zero input response. We found the zero state response of the simpler equation, the single input case equation, by finding a forced response and a piece of the natural response. Now, if this single input case difference equation was the real problem, if this is what we asked you to solve, we're done. Total response is just zero input response plus zero state response. But we didn't ask about this one, we asked about this other more complicated one, slightly more complicated. I got this extra term in here. What we need to do now is find out how do I take this information, that's the solution to this simpler equation, and make it the solution to this one. Answer? Zero input response doesn't change. Zero state response generalizes according to what's going on the right-hand side of the equation. Here's how that works. If you've got anything on the right-hand side except x of n, that's a general case difference equation. So what we do is find the zero state response for the single input case. We just put x of n on this side like we did. Make the simpler equation, find the zero state response, and then we're going to use linearity, superposition, and time invariance or shift invariance to find the zero state response of this more complicated one. And this didn't make quite so much sense in 228 when we made this argument, but now it does. We know if you put in x1 of n and get a y1 of n out, if I scale that x of n, I scale the y of n, right? That was homogeneity. If I add two inputs, their outputs also add. So I have a linear system, those two are true. I also know, so I can make a superposition combination of different scales and different inputs and just scale and shift their outputs the same way. That's when I have a linear system, these three things are true. If I have a shift invariant system, if x1 produces y1, x1 delayed by 1 produces y1 delayed by 1. That's shift invariance. So if I put in scaled and shifted versions of the input, I get scaled and shifted versions of the output. Well, the difference between this case and this case is just an input term. So we're going to use that same logic to say, if you know the zero state response for just a single input case, if my other equation has b times that, the zero state response for that more complicated one is b times the zero state response. If I have a delayed term in the x side, I'm going to delay my zero state response in a single input case. All the operations that are demanded by the right-hand side that we do to our input, the response is going to be those same operations done to the zero state response. That's why we broke it up this way, so that linearity and superposition and time invariance dictate how to take the simple answer and make it work for this. Okay? Once we generalize the zero state response, we just add it to the original zero input response and we're done. So let's do that. Here's our zero input response. Okay. We found the single input case zero state response, this mess, and our zero input response. The general zero state response, well, our general equation has x sub n plus x sub n minus 1. So we'll take the zero state response and we'll take a delayed by 1 version of it and add those two together. This is just this term says take the response and delay it by 1. There's the same thing. Everyone is n, I replace it with n minus 1. Don't forget the exponent. That's the zero state response of the general equation derived by linearity. If I had a 3 here, then I would have tripled this piece. Right? We scale and we shift. Anything that the difference equation says to do to the input, we do that to the single input case zero state response. Then for the total response, we add this whole thing to the original zero input response. The zero input response does not change between the single input case and the general case because the left-hand side didn't change. So we add this equation to this one, and we get the total solution to the response. Where the only thing that changes is notice I have a minus 1 times minus 1 half to the n here. I have a plus 2/3 times the same thing here, which gives me a minus 1/3 of it there. So this would be the total response of the general system to my unit step input and the initial conditions, all linear. Now what's with the color code? I put in a unit step, right? The forced response piece is the green, something that has that unit step shape. 4/3, 4/3, 4/3 delayed. So I put in 2, I got out 4/3, a little bit less. This other stuff, it's all got 1/2 to the ends. That all came from natural response. So all the green terms, all the yellow terms are natural response, part of the natural response of the system. And if you plotted it, we put in a 2, and we got on. Well, we got a 4/3. That's not right. Gotta look at that one. And we got a little exponentially thing going there. I'm gonna double check that. I don't like the looks of that. But you get the idea. Forced response, natural response. Here's how we're gonna do it. Try it for homework. It's gonna fill up pages. You're gonna hate it, but you'll love it later when we convert it to transform. I absolutely guarantee there will be a solution of a difference equation on the next midterm and the final exam, so don't skip over it. Give it a try over the weekend. We'll leave it up on Monday. See you then.
Yeah, when is the meeting?